robotics team. So we were here last year. We were the ones who had most innovative design. We've improved since then a little bit. So this year we're working not only improving more also on our design structure wise, but we're also focusing more so on our code base. Let's see, we stabilize grid-based navigation. So we're actually using the floor grids. Haven't actually saw anyone who presented who used that yet. To achieve, we've also gone into achieving ground robot detection as well as ground robot interaction and establish a strategy to interact with them. We've also, for the frame-wise, modified it to where it would be more robust and durable for long-term use. Overview. Next year, we're going to work on improving the strategy as well as creating a lighter frame and making a more modular-based code design. So, there's that.
Our overall team is divided into structures, electrical systems, and control systems. For this, this was 2 years ago. We did a fully 3D printed framework, and then we wanted to lighten it the following year. So this was Hank 2. We used carbon fiber in a lot of our 3D printed parts, and we did a lot of CNC for the mounting plates for sensors. And then this year we're working on a lot smaller frame. So we shrinked our frame down, but we increased the amount of, because we added a lot more sensors. This year we're using approximately 4 cameras, correct. And in addition to that, we are shrinking the overall size, like the width and the length of it down a lot more. But we're increasing height because we're adding another sensor module below it as well. This is our custom designed PCB board. We also integrated the kill switch, which can handle up to 200 amps, so we don't have any problems with overcurrenting and when we fire up all the motors when at peak. In addition to that, we also think we changed the overall layout. This is our third iteration of the kill switch and the power distribution board. We're also able to run from switching from 2 different power sources. So we're able to run from battery, and then we can plug in a AC input or DC input, and it'll switch directly into that. So it allows software to test our code directly on the system without removing any of it. So. We are using the Tiger motors, and then we're also using 40 amp ESCs and Pixox for stabilization. And then I'm going to switch it back to.
All right, so the high-level design on our code. We are decided for strategy-wise, take off, detect with we have a peripheral set of cameras, USB cameras, for visual system. We are detecting ground robots. If we cannot detect a ground robot, we are going to fly towards the center and try and find a better perspective on the ground robots. And then once we define the ground robot, we are actually localizing ourselves with the grids with the lower camera, and we try and localize the ground robots towards the grids, and we try and do set points where to go to the next one. Once we've achieved the set points, we've set it to interact with the ground robot if the orientation of the ground robot with our downward facing camera, if it's not facing the goal we want it to, we should interact with it until it faces it. So going more in detail for that, we are using 2 Odroid XU4s for that should be onboard computation. Yeah, it has 8 cores on it, pretty lightweight but really durable ARM processor. We have other sets of sensors. We have the Hakuyo for our LiDAR, for giving us altitude sensor for the guidance system. So we can detect navigation as well as obstacle avoidance. And then an array of webcams, USB webcams for our visual system. So we have here a video of our visual system. With our downward-facing camera, we are able to track the actual grids on the bottom as blobs. Now, these blobs can also, we draw lines across these blobs, and we have virtual lines across these blobs, and we detect all the intersections with these virtual lines. And so we're able to get a pretty robust system. As you can see down in the bottom right corner over there, the chair is kind of blocking the grid. So that would assume, say, something like a ground robot would be over a grid. It would still be able to detect it because it detects the lines that are pointing towards the intersection. Play the video. There you go. So as you can see, it's pretty good. A little bit noisy, but it's pretty stable compared to other methods such as the PX4 flow and guidance as well. So what we do is that we take that velocity, the average velocity of all the intersections of the grid, take the previous frame to the next frame where they move, average all of those things, and then find the velocity, the average velocity of the floor. Once we find the average velocity of the floor, we use our height data from our Hakuyo to figure out our altitude. Using trigonometry, we can figure out the exact velocity and therefore position of our craft. We use sensor fusion with the guidance sensor on the bottom to also help with that navigation localizer system. All right, so that was just the localizer node. We broke most of our code up into 4 nodes. The localizer node gives us a sensor fusion and a localized position, relative position to the grid. So the observer node is what handles all of the image processing data. So the image processing data is pretty high intensity. So we are modularizing that and having it handle with 2 odroids. We are detecting the grid for the downward-facing camera, and we also have 3 other cameras on the side to detect plates, colored plates. Once we localize ourselves to the grid, we can localize the plates relative to ourselves by projecting essentially a model of where the cameras are facing and from its perspective where trajectory-wise, where the target ground robot would be relative to our craft. The navigator node is essentially our AI, which then picks which target ground robot we want to interact with, or in this case, it's just the closest one for now. We pick just one ground robot, try to target that one ground robot until it follows it all the way to the goal line. So going through the goal line, to do that, it would take the downward-facing camera. We have a system that would actually detect the orientation of the ground robot using the shape of the plate itself. So we had a little issues when we changed the plate design. But we kind of solved that, I think. But now, so once we found the orientation of it, we know we've been tracking our orientation of when it flies. So with that orientation, we know the direction of the goal relative to our vehicle. And we also know the rotation of the ground robot relative to our vehicle. So therefore, we know if the ground robot is facing the goal. To actually interact with it, we would check if the ground robot is facing not towards the goal, plus or minus a range angle. And then if it's not, try to interact with it until it faces that, and then let it do its thing. The controller node uses PID loops, so therefore the navigator is just a simple set point to a essentially relative grid location. So we simply give it x and y coordinates in meters, and the controller node would send a PID loop to try and navigate the system to the desired set point. So this is a high-level design of our control systems. Well, actually, no, this is low-level design. It has representation, can't really see it all, but this is essentially how we were able to design how each system would interact with each other, how each possible states it would handle, and going from localizer, bottom right corner, observer, top right corner, navigator, top left corner, our AI, and the bottom would be our controller. Any questions? Right, so we've done some simulations. We've gotten localization down in the test data using just hovering cameras. Actually flying, we had issues with the actual hexacopter physically. So we weren't able to actually test fly a lot of it. I was planning to test fly at least a whole month of it, but got delayed quite a bit. We modified quite a bit of the code for it to be able to handle less cameras. We actually designed it to have 7 cameras all around, so no blind spots at all at that point, unless of course it's really far away. So that's why we have the essentially traversing towards the middle to find any ground robots. Now, right now we're limited to 3 because we had issues